All right, lastly, we are checking our shear demand and making sure that the shear capacity of our stem is adequate. For retaining walls, at least any retaining wall I've ever done, you really are gonna have a phi Vn just equal to phi Vc. That means you are not using any shear reinforcement V sub S. That would be some kind of like stirrups in the wall horizontally. That just, I think if you ever design something like that, you should be talking with your project manager or your principal, because that is very, very, very uncommon, really hard to construct, expensive to construct. But I obviously don't know every scenario for retaining structures, so there may be instances where that's absolutely applicable. But if we find out that we don't have enough shear capacity just from the concrete alone, ultimately I wouldn't insert steel. I would increase the thickness of that stem to make things work out. Phi Vc equals the following. And again, this is a big change upcoming in the new code cycle where this equation completely changes. So make sure you keep an eye on that. But for this one, it is the 31814 manual that we are using for the ACI. Lambda equals 1.0. That's just for normal weight concrete. So don't sweat it too much. I think that's ACI table. Wow, is it gonna be off the top of my head? 19.2.4.2. See if I'm right, check that out. And also phi is going to equal 0.75, and that is ACI table 21.2.1. Phi Vc, all that plugged in gets us the following. Make sure you're using D and not H when you are calculating your shear capacity, which spits out 17.07 kips per foot of wall. But what's our demand? Well, our demand, if we scroll back up here, go all the way back up, is simply this portion here, if I go highlighter, of the equation here and here to get our shear demand. So we are not multiplying that force times our moment arm anymore. So this portion of the equation and this portion of the equation go away. All of that gets us 9,000, oh, sorry, I'm gonna leave it in kips, 9.8 kips per foot of demand. All right, so that is significantly less than our shear capacity due to just the strength of the concrete. And if I draw our little diagram here, ultimately I took shear, if I go blue, about the base, but you could, if you needed to sharpen the pencil here, you can actually take shear demand D from the face of your element. So which would then ultimately, when we're talking about our demands here, would reduce your demand if you're finding shear at this point. So if you needed to sharpen the pencil, that's one additional thing that you could do. We don't even need to do that here today, but just wanted to point that out. But what about AV min? We want to make sure we're code compliant, right? Well, for slabs, one-way slabs, AV min is not required when phi Vc is greater than Vu. So AKA, if your concrete is stronger than the demand alone, then you're done. For beams, if you all remember, phi Vc over 2 needs to be greater than Vu in order to avoid AV min criteria. So that's where, even if the strength of your concrete is adequate, you may still need to provide shear reinforcement in your concrete member. But for slabs, that is not the case. It's just straight up, if you have enough capacity, you're good. If you want to check it out yourself, this is ACI 7.6.3.1, because there are different requirements for, I think, precast and I think one other thing in there, but this is just regular concrete, so we know that we're good to go. And to finish things off, I've given a little sketch here showing the orientation of our steel, as well as the sizing and spacing of all of our steel, and a little bit about the clear cover. Something you would regularly see on a set of structural drawings. Very legible for the contractor to construct. And one thing we want to make note of is that your longitudinal bar, you want to be on the outside face of that mat. The closer to the edge of your concrete stem, the more capacity you're ultimately getting in your structure. If it were to be on the inside and your temperature and shrinkage reinforcement was on the outside face of that mat, it would be less efficient of a structure, just by a little tiny bit in terms of capacity. But hey, you might as well get the full strength of your design, especially when all it takes is just the order in which to construct it. So remember little things like that. I didn't go into kind of development of the steel down into the base, so there is that check that would still need to happen, but today I think we're running long here, and it's just ultimately all of the checks required for the strength of your stem wall. If everything you saw here sounded great today and you learned a little something, leave a like down below, consider subscribing. I'd love to see you in here again sometime soon. And if you want to go above and beyond, you don't have to, but you could, join Team Kestava. Every little contribution helps me create more content, reach more engineers, and hopefully explain things better. Oh, my dog is shaking in the background. He's getting excited. I'm getting excited. We're over 10K engineers. But before you go, obviously, if you're still craving some more engineering knowledge, why not check out some of these other videos? Or are they over here? Or are they up above me? They're gonna be somewhere, so click on those, check it out, see what I have to offer, and until next time, peace.